Comparative planetology. How's that for a riveting phrase? That's what we're going to be doing a lot of. And whatever it means, right? Well, you know what it means. Both words are not mysteries to you. It means that you can learn a lot about a thing by comparing it to other things that are in the same class, like birds, right? I'm a bird guy. I like birds. And warblers say, the way to really, warblers kind of look alike to those who haven't looked at them a lot. Right, they're all kind of yellow, all kind of small, but they got some blue on them too, a little bit of green. So warblers is a kind of bird, but you learn a lot by sort of having one and keeping one in mind, and then comparing others to it. Right, and we're going to do that with the planets. We're going to start with the Earth, and then we're going to compare all the other planets to it. All right, we're going to compare all planets to the Earth because it's the one we know the best. It's the one that has been very good to us over these many centuries. And so it's the one we're going to start with. But we're not going to start with it now. We're going to talk about how we're going to go about this. We're going to start with Earth on Tuesday, tomorrow. But for today, we're going to talk about what I mean by comparative planetology and how we're going to go about comparing the planets to each other, and especially to the Earth, because it's our reference. But we can, of course, compare Mars to Venus and things like that as well, comparing planets. We're going to do that by using a table, and I provided for you a table on Canvas, and I want you to print it out, and as we go through the planets I want you to write the numbers down, because we're going to be using numbers. It's science, and astronomy is highly mathematical, so we're going to be using numbers to compare the planets. And I'm not going to be able to go through every planet over the next couple of weeks, every planet in great detail. So what we're going to do, because it's simply time, even when I teach this class in a face-to-face format, I don't have time to do all the details about every planet. So what I'm going to do is use this table, this comparative planetology table, to start our conversation about each planet. I'm going to find one number from each planet which is interesting, and I'm going to talk about that number. Instead of talking about everything about the planet, we're just going to use a single number. Now what that table does is for every planet, what your comparative planetology table does is for every planet, we're going to look at, how many numbers do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoa, that looks nothing at all like a 9. Let's see if I can do that correctly here. Look at 9 numbers. So your table has planets down the left-hand side and these 9 values across the top, and every planet has these 9 values. And what these 9 quantities are for every planet are these. Let's write them out. Number 1. Semi-major axis A. We've seen the semi-major axis. We talked about Kepler's laws, right? That's the average distance between the planet and the sun. And the units we're going to use for this are going to be in AUs. So for the Earth, that number is going to be simply 1. Okay? The second number is going to be the orbital period. Okay, that's going to be capital P with a sub O for orbital. Okay, that's how long it takes for the planet to go around the sun once, to make a complete orbit of the sun, and that's going to be in years, Earth years, standard sidereal Earth years. Okay. So, for example, Jupiter would be 12, because it takes 12 years for the Jupiter to orbit the sun once. The third number, the mass, how much stuff is in the planet, and we're going to use symbol M with a subscript of a circle with a circle with a cross through it. That symbol, the circle with a cross through it, is the symbol for the planet Earth. So when you see it, that means planet Earth. So if Jupiter has 100 times the Earth's mass, we would say that its mass is 100 m sub Earth. Okay. Venus has about the same mass as the Earth, so it's approximately 1 m sub Earth. Okay. So the units we use for this number are going to be Earth mass units, with the mass of the Earth as a single, as one. The radius, usually it's the radius that's given and not the diameter, because radius shows up in all kinds of formulas that the diameter does not. So we use radius instead of, which is of course half the diameter. And we're going to use Earth radii for that. R sub Earth. So Mars, for example, is about 1/3 the size of the Earth, and so its radius will be 1/3 R Earth. Jupiter is about 10 times further across than the Earth. You can fit about 10 Earths across Jupiter, so its radius would be 10 Earth radii, or 10 R sub Earth. So our unit again is the Earth. Number 5, the number of moons. We've already talked about this already, but I'm going to use it in the table anyway. Okay, I'm just going to call that number N. Okay. Oh, the mass is given the symbol M. The radius is given the symbol R. Okay. Every one of these on the table, you're going to have these symbols: A, P naught, and so forth and so on. Okay. Number 6. Number of moons. The rotational period. The orbital period was P sub O. Rotational period is going to be P sub R. Actually, I'm going to make it lowercase r so it doesn't get confused with radius. P sub R. And that's going to be in Earth days. Okay, ED. Okay. Takes Venus about 80 Earth days to rotate once. Okay, so that would be 80 in that case. And these are sidereal days. Technically, they're 23 hours and 56 minutes, but you can think of them roughly as solar days, our standard colloquial day. 7, the density. And the symbol for density is the Greek letter rho. Looks like a backwards 9. Okay, and density tells you how packed the planet is, how much stuff there is for a given amount of space. Lead is very dense, and balsa wood is not dense at all. Okay, you can have a cube of balsa wood this big and a cube of lead the same amount. They both occupy the same amount of volume, right? But the lead is much heavier because it's much denser. The neutrons and protons and other ions are packed together really tightly. So the more packed in the material is, the higher the density. Okay, and the units for this are going to be kilograms per meter cubed. The Earth is going to be about 5,000 kilograms per meter cubed. So if you had a cubic meter, let me see, where'd my meter stick go? Did I lose my meter stick? I thought there it is. Let me get my meter stick. So if I had a box this big on a side, okay, so a meter wide, a meter deep, a meter high, a cube this big on a side, and I had an average amount of earth in there, that would have a mass of about 5,000 kilograms. So it's 5,000 kilograms per cubic meter, right? that much space, that much volume is known as a cubic meter. And 5,000 pounds is a lot. I mean, 5,000 kilograms is a lot. It's about 10,000 pounds, about 5 tons. So put that earth and fill that box up with earth, about 5 tons of earth. Okay, that's the density of the planet. On average, near the core, it's more dense than that. Out here near the edge, it's, near the core, it's more dense than that. As you go deeper in the earth, it gets more and more dense. So down near the core of the earth, it's more dense than 5,000. Up here near the surface, it's less dense than 5,000. The 8th thing is going to be the axial tilt, and that's going to be in degrees. For the Earth, it's 23.5. Remember, that's the tilt of the Earth. It gives us the seasons. We talked about that last week. Actually, the first week we talked about that. The tilt of the Earth gives the seasons. That tilt's about 23.5 degrees. Sometimes this is known as the, in scientific circles, it's known as the obliquity, which I prefer that word because it's fun to say. Obliquity. And the 9th is the magnetic field. You all know magnetic field of the Earth, right? That's what makes our compasses point north, right? There's a magnetic field all around you all the time, every moment of your life, every day of your life. You've been walking around in an invisible, you can't taste it, you can't see it, you can't touch it, you can't feel it, but it's there, the Earth's magnetic field. Symbol for that magnetic field is B, believe it or not. Can you believe it that the actual physics symbol for the magnetic field is B? There's a reason for that, but I'm not going to get into it right now. And the unit we're going to use is the magnetic field of the Earth as a standard. So Mercury's magnetic field is less, so it might be 0.01 B Earth, whereas Jupiter's is enormous. It might be 900 B Earth. But the Earth's magnetic field is taken as the unit, the standard. So what we're going to do in the future, as we go through the next week and a half, really, we're going to be looking at planets, and we're going to be using this table, and we're going to be filling it out as we go. I want you to, hand write as we go, print it out, and have it in front of you. And we're going to be filling this out. And we're going to do the Earth in a little more detail. It'll take 2 days for the Earth, but the other planets we're going to go a little bit faster with. And the way I'm going to do that again is I'm going to take this table and we're going to pick one number from this table, and we're going to talk about that number for each planet. It'll be a different number for each planet. Every planet's got some weird numbers. I'm going to pick my favorite weird number for each planet, and we're going to use that number to talk about sort of start our conversation. Okay. No planet will get more than 2 videos, so we have to make it we have to sort of cut down. We can't say everything. Anyway, I think if we said everything, I think it would get a little tedious, talking about the interiors of all 9 planets in detail. Listen to me, 9 planets. I'm so silly. Talking in detail about the interiors of all 8 planets would get tedious. Okay, so we're not going to do that. We're going to pick a number from this table for each planet and talk about why that number is interesting. That's going to be our jumping off place. So we're going to be doing a lot of fun comparative planetology